Investigate the graph of y equals some constant a times f of x. We will do this by hand, using a table, with technology, and then generalize. You will need graph paper or a page of grids, and you can download that at this website. This is part of the Family of Functions series. We will start our investigation with y equals x squared. So go ahead and graph y equals x squared using the parabola dance. Press pause until you're finished. So we'll start at the origin. 0 squared is 0. Write 1 up 1 because 1 squared is 1. Write 2 up 4. Write 3 up 9. And then on the other side, left 1 up 1 because negative 1, the quantity squared, is 1. Left 2 up 4. And left 3 up 9. Notice that we could have also graphed the last 3 points using symmetry about the y-axis. Go ahead and connect the points, and we have y equals x squared, our parabola. Now, keeping an eye on this parent function here, I want you to graph y equals 2 times x squared. Make a table with 5 rows using these x values. Complete the table. Press pause until you're finished. So here's how I calculated the values for y here. You can see them here. Pause if you need to do so. And these are the values we got for y. Now plot those points, and again press pause until you're finished. So those are the points plotted. Now connect the points, and again press pause. And this is the graph of y equals 2x squared compared to the graph of y equals x squared, the parent function in blue. How are the graphs similar? Well, they do have the same shape. They're both a parabola-looking curve. And how are they different? Well, press pause until you're finished thinking about that. The green parabola is narrower than the blue parent function. You might also say that the green parabola goes up faster than the blue parent does. Let's compare and contrast using tables. Here's our y equals x squared table, and let's compare it to y equals 2 times x squared table. Press pause until you're finished. Notice here that the x coordinates are identical. Look at the corresponding y coordinates. Press pause until you're finished looking at those. Notice from 4 to 8 times 2, and also notice the 2 times in the equation. Similarly here, 1 to 2, 0 times 2 is of course 0, 1 to 2, 4 to 8. All the y coordinates are doubled, and that comes from the equation. So we say that the graph of y equals 2x squared has a vertical stretch of 2 from its parent function y equals x squared, a vertical stretch of 2. The dilation factor is 2 for y equals 2 times x squared. Call that a dilation factor. You can see it in the graph. You can see it in the table for sure. And you can see it in the equation, the dilation factor of 2. We're going to repeat the same exercise, but with a different equation this time. Keeping an eye on y equals x squared, we're going to graph y equals 1/2 times x squared. This time we're going to use a table with 7 rows. These are our 7 values for x. Please complete the table. Press pause until you're finished. Again, these are how the values were calculated here. Press pause if you need to read those more carefully. And putting those values in the table using fractions instead of decimals. Go ahead and plot these points. Pause until you're finished. Plotting those 7 points, we get a curve like this. Connect the points. Press pause when you're finished until you're finished. And it looks like another parabola. Y equals 1/2 x squared in green there. So again, how are the graphs similar? They do have the same shape. How are they different? Again, I'd like you to go ahead and press pause until you finish figuring that out. The green parabola is wider than the blue parent function in this case. We could also say that the green parabola goes up slower than the blue parent function because of that 1/2. Compare and contrast using tables. Again, we'll start with the y equals x squared table. Press pause until you're finished comparing and contrasting those. Looking at the x column, the x coordinates are identical. Look at the corresponding y coordinates. Press pause until you're finished looking at those. And you can see that each y coordinate is multiplied by 1/2 in blue to get the green function. So the parent y value times 1/2 gives me the function we're looking for in each case. And notice where that times 1/2 came from. All y coordinates are halved. Terminology, we say that the graph of y equals 1/2 x squared has a vertical shrink of 1/2 from its parent function y equals x squared, and the dilation factor is 1/2 for this equation. You can see it in the graph. It's going up slower by a factor of 1/2. You can see it in the table. Everything is halved. The y coordinates, I should say, are halved. And you can definitely see it in the equation. We're going to do this one more time, but with a different equation. And in this time, we're going to use a negative number for the coefficient of the parent function. Again, keeping an eye on y equals x squared, the parent function, graph y equals -2x squared. We're only going to use a table with 5 rows this time. Please complete the table with these x values. Press pause until you're finished. Here's how we calculated those values. Press pause if you needed to check any of them. And then place them in the table. Go ahead and plot these points. Press pause until you're finished. Here are those 5 points plotted. Go ahead and connect them, and again press pause. And here is the graph of y equals 2 times x squared. How are the graphs similar? How are they different? Press pause until you're finished thinking about that. The graphs are the same shape. One's opening up and one is opening down. How are they different? The green parabola is narrower than the blue parent function. Again, one up, one down. The green parabola is below the y-axis, while the blue one is above, except for sharing the origin. Let's compare the graph of y equals -2x squared, the green one, with y equals positive 2x squared. So let me go ahead and graph that for you. What do you notice? Press pause until you're finished. Notice here, look at these 2 points. Look at these 2 points. In fact, look at all the points. The graphs are reflections of each other about the x-axis, using the x-axis as a mirror images of each other. Let's investigate the graph of y equals a times f of x for other functions besides y equals x squared. And we're going to do this using technology. So here we have the graph of y equals absolute value x. It's going to be in dashed blue. And in green is y equals a times the absolute value of x. In this case, a is 1. This is where we'll control the slider values. Please look at the graph and at the table values here. Here's the blue parent function. Here's the green function values right here. Notice they're identical right now because a is 1. So let's increase a to 2. So here's y equals 2 times the absolute value of x. And you can see that it's narrower. You can also see what is happening to each of the y coordinates there. A is increased to 3, narrower still. Look at the corresponding y coordinates. A equals 4, a equals 5. Kind of get the idea there. So let's go down and let's look at values between 0 and 1. Now I've changed the slider so it steps down by 1/8. So let's go ahead and make a equal to 7/8. Notice it's a little bit wider, the green function. If I make it 3/4, y equals 3/4 absolute value of x. Y equals 5/8, y equals 1/2. Now this is y equals 1/2 the absolute value of x. Notice what's happening to all the y coordinates. Let's make it 1/4. Again, wider still, and look at the y coordinates. And then going down to 1/8. All right, returning back to a being 1. This time I've changed it, so we're going to look at negative values for a, negative coefficients, using a step size of 1. Now if I make a equal to 0, of course it's just the line, y equals 0. But when a is -1, notice that it's symmetric, or a reflection of the graph y equals absolute x, using the x-axis as the line of reflection or the mirror. A equals -2, it's narrower, but it's reflected, it's negative, opening downwards. A equals -3, look at the corresponding y values if you weren't looking at them before. A equals -4, even narrower, but again, opening downwards, and look at all the corresponding y values. Now we're going to look at the parent function being y equals the square root of x. That'll be the blue dash function. The green one is the one that is controlled by this slider right here. Right now you can see that the y coordinates are the same. So let's increase a to 2. Y equals 2 square roots of x. Notice the y coordinates, especially the ones that are whole numbers, are easy to see. Y equals 3 times the square root of x. What's going on in the graph, what's going on in the table. So let's go ahead and look at values between 0 and 1. Here the step size is going to be 1/4. So let me make a smaller. So there's y equals 3/4 times the square root of x. Y equals 1/2 the square root of x. Notice how it's not going up so fast. Y equals 1/4 square root of x. Almost looks like a straight line, but it is not. Now let's look at the square root function where the coefficient is negative. So starting with, and I'm going at step size of 1/2. So there's 1/2 square root of x, there's 0 square root of x, which is still the line y equals 0. But here's y equals -1/2 the square root of x. Y equals negative the square root of x, which is the reflection of line y equals the square root of x, or the curve y equals the square root of x, the reflections of one another. Y equals -1/2, notice it's getting taller but in a negative direction. Y equals negative 2 square root of x. And again, looking at the table to see what's happening to the y values as well. Now we're going to use for our parent function this piecewise function here called f of x. And the green function is controlled by this slider right here. The step sizes will be 1 here. So y equals 2 times f of x. Notice what's happening to the curve and what is happening in the table when a is 2. When a is 3, notice what's happening to the graph and what happens to each y value in the table. And 4 kind of goes off the screen. So let's now go ahead and look at values between 0 and 1. Using a step size of 0.25 or a quarter, here's y equals 3/4 times this f of x. Here's y equals 1/2 times f of x, y equals 1/4 of f of x, and y equals 0 f of x. Next, we'll look at negative values for a. So we'll start with a being negative 1/2. This is y equals negative 1/2 times f of x. Y equals the opposite of f of x, and you can see again it's the reflection of this curve about the x-axis. Y equals negative 1.5 times f of x. Y equals negative 2. Notice again the graph. Notice the table values. Negative 2.5, negative 3, and so on. Here we took some screenshots to be able to compare these and contrast these. Here's y equals x cubed, the parent function in dashed blue. 1/2 x cubed, note how it's changed. And we also picked the value here so you can kind of compare. Notice the y values are half of what they were before. Y equals 1/4 x cubed compared to x cubed and also 1/2 x cubed. Notice what's happening with the y values there. Y equals 2x cubed, a little bit narrower. Negative 2x cubed. And then finally looking at y equals negative 1/4 x cubed. See how these are reflections of one another about the x-axis. Press pause as needed. Here we'll look at the y equals the square root of 25 minus x squared, a semicircle. It's in dashed blue, that's the parent function. 1/4 of that, notice what happened to the semicircle there. 1/2 of that, what it looks like. And again, look at the table values so you can see what's going on there. Y equals 2 times the square root of the quantity 25 minus x squared. Not really a semicircle, more looks like an arch of some sort. Notice what's happening with the y coordinates. Y equals negative 2 times the square root of the quantity 25 minus x squared. These two green curves would be symmetric about the x-axis, reflections of one another. And then finally, y equals negative 1/2, that square root. Notice how that compares to this one. Go ahead and press pause so you can look at the graphs, look at the tables. And the last one we're going to look at is this generic function, y equals f of x, a piecewise function. It's in dashed blue. Y equals 1/4 of f of x. Notice what the graph looks like compared to the parent and what happens in the table. Y equals 1/2 times f of x. Y equals 2.5. I went with 2.5 instead of a whole number this time and see what happens to the y values. Y equals negative 2.5 and how it compares to y equals positive 2.5 times f of x. And then y equals the opposite, or negative 1/2 times f of x. So you can see how those compare as well. Press pause as needed. Let's generalize what we've learned. The graph of y equals f of x, the parent function, and the graph of some constant a times f of x are similarly shaped curves. If that coefficient a is greater than 1, the graph is stretched vertically with a dilation factor of a. If a is between 0 and 1, the graph is shrunk vertically with a dilation factor of a. If a is negative, graph y equals the absolute value, making that positive times f of x, and then reflect that graph about the x-axis. Keep in mind that for all of these, each y coordinate of the parent function is multiplied by that value a. Now you try one. Graph y equals 2 times the cubed root of x for the practice. Press pause to do this and then resume when you're finished to check your answer. And here is y equals 2 times the cubed root of x, kind of stretched out a bit. Each y coordinate is doubled from the regular cube root function.